Hello viewers, in this video we are going to learn about instruction cycle in basic computer organization and design. Let us now first discuss what is a program. A program, it contains collection of instructions and are stored inside the memory, right? Just I do like to highlight one of the important point about memory. Since the basic computer follows stored program organization, programs as well as operands are stored inside the same memory in different portions of it, right? Let us now discuss how every instruction that are stored inside the memory is being executed. That is, in a basic computer, when a machine instruction is executed, it has to follow these phases. In the first phase, the instruction from memory is fetched, and in the second phase, the instruction is decoded. And in the third phase, the effective address of the operand is read from memory if the instruction has an indirect address. Here, the effective address of the operand is required in order to fetch the operand whenever a memory reference instruction is executed. Okay, and this third phase is applicable only for the memory reference instructions and not applicable to register reference and input-output instructions. And in the next phase, the instruction is getting executed. Okay, so like this, every instruction has to follow the above four phases when it is getting executed, and this cycle starts again right from step 1 in order to execute the next instruction in the program, and this process is continued until the halt instruction in the program is encountered. Let us now discuss in detail about fetch and decode phases of an instruction cycle. Let's discuss this concept with an example illustration which is shown here. Just assume that a program having a number of instructions whose first instruction is stored into the memory in the address 255 and the halt instruction is stored in the address 300. Okay, the program is stored in the memory. Okay, before starting the execution of the first instruction in the memory, there are two micro operations need to be performed. Those are program counter register need to be loaded with the address of the first instruction in the program, and the sequence counter also must be set to 0. Okay, these two micro operations need to be performed before starting the instruction cycle of the first instruction in the program. Here, in order to in order to generate the timing signal from T naught, freshly for the next instruction cycle, the sequence counter must be set to 0. Okay, these two micro operations need to be performed before starting the instruction cycle of the first instruction in the program. Okay, just assume that these two micro operations are performed. Now, the instruction cycle of the first instruction shall start. Okay, so in the next clock cycle, the timing signal that will be generated will be T naught. So during that time, program counter value need to be transferred to the address register. Okay, what is the program counter value as of now? It is holding the address of the first instruction, right? That is 255. Now, during the timing signal T naught, that content from program counter to it has to be transferred to address register. So once it is transferred, the address register will be now holding the address 255. Okay, this transfer of content from program counter to address register is required because address register is the only register that is directly connected to the memory. So here you can observe in the common bus system, this address register is the only register that is directly connected to the memory unit. That's why before performing any memory operation with memory unit, the memory location from where the memory operation is performed, it has to be loaded into the address register. So from that memory address only, the corresponding memory operation can be performed. Okay, so that's why the transfer of information from program counter to address register must be performed during the timing signal T naught. Okay, and once the address is loaded into the address register in the next timing signal T1. What are the micro operations need to be performed? The content from the memory address pointed by the address register from memory, the content has to be transferred to the instruction register. Okay, that is instruction is fetched from the memory address pointed by the address register and loaded into the instruction register. Okay, this operation need to be performed, and also the program counter value need to be incremented during the same timing signal. Okay, during the same timing T1, the transfer of information from the memory address to the instruction register need to be performed, and also the program counter value also need to be incremented. The now when the program counter is incremented, what will be the value it will be holding? So earlier it was having 255. After the increment, it will be holding 256. So now it is the address of the next instruction in the sequence. Okay, now the program counter is ready for the instruction cycle of the next instruction. Okay, these two micro operations need to be performed in the timing signal T1. Okay, and micro operations which are performed during T0 and T1 are related to the fetch phase of an instruction cycle. Okay. And the micro operations which are performed during the timing signal T2 are related to the micro operations to be performed during the decode phase of an instruction cycle. Okay. So at the end of the timing signal T1, the instruction which is fetched from the memory is available in the instruction register. Right. Now during the timing signal T2, it has to be decoded. Okay, how it has to be decoded? The 12 to 14 bits of the instruction register, it has to be decoded using the 3 by 8 decoder. So when it is decoded, it will generate the output lines between D0 to D7. Once it is decoded, it will generate the output lines D0 up to D7. Any one of the output line among D0 to D7 will be active. And the 0 to 11 bits of the instruction register are transferred to the address register. Whereas 15th bit of the instruction register is transferred to the I flip-flop. Okay. So these are the three micro operations need to be performed during the timing signal T2. Students, here you can observe the common bus system here illustrated in this diagram. It is the selective portion of the common bus system what we earlier studied in the previous video. Okay, here this common bus system is here. It is given in order to highlight the how the timing signals are connected to the components such as selection inputs of the common bus, memory unit, other registers which are required to perform the fetch and decode phases of an instruction cycle. Here, what are the components are required to perform the micro operations during fetch and decode phase? Address register, program counter, memory, right? So, address register, program counter, and instruction register also, right? So, only these components are included in this common bus system. Okay. So, let us now relate the micro operations which are performed with the timing signal which is specified in this diagram. Okay. During the timing signal T0, what is the operation to be performed? The content from program counter to address register need to be transferred, right? So in the common bus system, to enable this transfer, the selection signal values must be 0, 1, 0. So 0, 1, 0, it is the binary equivalent of the decimal number 2 which is specified along the program counter register. So once the selection signals are set 0, 1, 0, it will initiate the transfer from program counter, and so once it is being transferred to the bus, then it has to reach the address register, right? So immediately the load signal of the address register need to be enabled in order to load the content into the address register. So these two operations these two micro operations need to be performed during the timing signal T0. You can observe here during the this timing signal T0 is connected to the load signal of the address register and the selection input lines of the bus. Okay. Whereas coming to the timing signal T1, what are the micro operations need to be performed? The content from the memory address need to be read and it has to be loaded into the instruction register. So to initiate the transfer from memory address, the selection input lines must be having the value 111 because 111 is the binary equivalent of the decimal number which is specified along the memory unit in the common bus system. And in addition to the selection lines, and the read signal of the memory unit also must be enabled. So with these two signals, the memory unit can transfer. The memory unit will transfer its content over the common bus, and in order to receive the content, the instruction register load signal need to be enabled. So you can observe here the timing signal T1. It is connected to the selection signals which activates the um, memory unit. Okay, 111. Its values need to be 111, right? So the timing signal T1 is connected to the selection input lines of the bus, and you can observe the T1 is connected to the read signal of the memory unit as well as the load signal of the instruction register, as well as in addition to this transfer program counter also value also need to be incremented, right? So you can observe it is also connected to the program counter increment signal. Okay, so now you can understand that how the timing signals are connected to the components of the processor in order to achieve the micro operations required during the different phases of an instruction cycle. Let us now discuss how to determine the type of the instruction in order to carry out the micro operations after the decode phase of an instruction cycle. Here in this flowchart, the micro operations which are performed during the fetch and decode phase of an instruction cycle, that is during the timing signal T0, T1, T2, T3, just now we discussed, right? So all those micro operations are specified here. You can also observe here before the starting of the instruction cycle of the first instruction in the program, the sequence counter is set to 0, and also you can assume program counter is also pointing to the first address of the first instruction in the program. Okay, so after doing this micro operation only, the instruction cycle of the first instruction starts, and here up to this step we already had discussed. Okay, let us now discuss the type of the instruction. Okay, how can we determine the type of the instructions? We know very well there are three type of instructions we have already learned in basic computer. Those are memory reference, register reference, and input output instruction. Yeah, after the decode operation of the instruction, if D7 output line of the decoder is set to 0, then it is known as a memory reference instruction. Um, then D7 will not be activated. Then D7 will not be activated if the input to the decoder values are not 111. Then D7 will not be enabled. In other words, we can say that D7 will be enabled only when the input to the decoder are all set to 111. Okay. In such case, D7 will be enabled. In all other cases, if input is not equivalent to 111, in all other cases, whenever it is 000 to up to 110, in all other cases, except D7, one of the output line from D0 to D6 will be active. Okay, since this opcode part of the instruction is very helpful to determine the type of the instruction. So when D7 is active, so the output part contains 111. What that is the meaning. So when D7 is active, it can be of either a register reference or IO instruction. When D7 is not active, that is when output part contains 000 to 110. then only D7 will not be active. In such case, the type of the instruction is determined as memory reference. Okay, when D7 is equivalent to 0, then it is known as memory reference, and D7 is set to 0 only when the opcode is not equivalent to triple one. Okay, let us now focus on this memory reference instruction. Then after that, we will come back to the rest reference or IO instruction. Okay, coming to the memory reference instruction, uh, the type of the operand which is specified in the address part of the instruction, it can be of two types. It can be either direct address or indirect address, that is determined based on the 15th bit value of the instruction. So this 15th bit is transferred to the I flip-flop, right? I flip-flop of the control unit. Now the control unit observes the I flip-flop value. If it is equivalent to 1, then the control unit initiates the micro operations, to, that is to transfer the address, effective address of the operand to the address register. Okay. In order to achieve this micro operation, the control unit has to set the selection input lines of the bus into triple one, as well as, since it is the memory operation, the read signal of the memory also must be active. Okay, so when these two are set, enabled by the control unit, and the load signal of the address register also enabled, then this micro operation, that is transfer of effective address from the address specified by the address register from the memory, it can be transferred to the address register. Okay, that is the effective address. Now it is available in the address register. Okay. Whenever the I flip-flop contains the value equivalent to 0, then nothing is required to be done during the timing signal T3, because already the effective address of the operand is directly available in the address part of the instruction. So there is no need of fetching the effective address of the operand to the address register. Okay, so during that T3 timing signal, nothing is required if the address part of the instruction contains direct address. Okay, but when it is containing the indirect address, effective address of the operand need to be transferred to the address register. Okay. And now the corresponding memory reference operation can be executed, and the operation is determined. The memory reference operation, which need to be determined based on the opcode part of the instruction. Okay, so after performing that particular memory reference operation, the sequence counter need to be cleared in order to initiate the timing signal freshly from T0, which is required for the execution of the next instruction. Okay, so in the next instruction execution, the instruction cycle must start with the fresh timing signal from T0. So in order to achieve that, the sequence counter value need to be set to 0. Okay, let us now discuss the other part where D7 is set to 1. D7 is set to 1 only when the input to the decoder are all set to triple one. Then only D7 will be active. Okay. So here you can observe the register reference and our input-output instructions. Though the opcode part contains a triple one, the type of the instruction is determined based on the 15th bit. Okay, if 15th bit contains 0 value, it is known as rest reference instruction. If the 15th bit contains the if the 15th bit contains the value 1, then it is known as input-output instruction. Since those values are transferred to the I flip-flop of the control unit, the control unit only takes the content from its own components, that is I flip-flop only. Okay. So when I flip-flop is 1, then it is known as IO instruction. When I flip-flop contains 0, then it is known as rest reference instruction. The corresponding IO instruction or rest reference instruction is executed during the timing signal T3. And at the end of the instruction execution, sequence counter also cleared. in order to initiate the instruction cycle of the next instruction with the timing signal T naught. Okay, here you can notice that number of timing signals required for performing the memory reference instructions are T4. But for executing the register reference or IO instruction, only T3 timing signals are sufficient, because here fetching the effective address of the operand is not required in case of uh, IO instruction and register reference instruction. Okay. Here you can see the symbolic statements which explains the concept what we discussed now. Those are symbolically represented. That is, when a D7 is set to 0, when D7 is set to 0 and I flip flop value is 1, then during the timing signal T3, the content from memory from the location hold by the address register is transferred to the address register. That is the effective address read from the memory to the address register. Okay, that is performed during the timing signal T3. And when D7 is set to 0 and I flip flop value is 0, and during the timing signal T3 nothing is performed. Whereas when D7 is 1, D7 is 1 and I flip flop value is 0. Then during the timing signal T3, register reference instruction is executed, and during the when D7 is set to 1 and when I flip flop is 1, during the timing signal T3, the corresponding IO instruction is executed. So the operation, the concept what we have learnt in the flowchart are symbolically represented here. Students, if you find this video useful to you, kindly subscribe this channel. Students, in this video we learnt about the instruction cycle. If you find this video useful to you, kindly subscribe this channel. Thanks for watching.